Dr. Ault has been on our faculty here at USU for 10 years now. She started her career and was trained fantastically as a student in geochronology, among other things, and using geochronology to figure out the histories of rocks and of minerals and of landscapes. And then as Alexis did a postdoc and other things, she became a pioneer in new methods of doing geochronology, specifically on rocks that are in fault zones, to figure out potentially histories of faults and earthquakes. And then more recently, Dr. Ault has sort of become the lead in an earthquake science group here at USU, and she is doing multidisciplinary work more broadly on what are the processes happening in faults and during earthquakes. And that's, I think, what Alexis is going to talk about today. So let's welcome Dr. Alexis Ault.
Okay, thank you so much, Joel. And also I just want to say a big congratulations to Blair. Thank you for your service. Thank you so much. Okay, this evening in our Back to Basics series, we're going to learn about energy transformations that happen during earthquakes, okay? Energy transformations that happen during earthquakes. So I want to see a raise of hands. Who in this audience has felt an earthquake? All right. Okay. All right. What did it feel like? What did it feel like? Does someone want to offer a feeling as they were experiencing that? Yes. Wait, sorry, say that again. Vibrating. Vibrating. Anyone else? What did an earthquake feel like? Yes.
It was very disorienting.
Disorienting. Yeah. Raise your hand if you felt shaking. Yeah, some shaking. All right. Did anything fall off bookshelves or things like that? Window crack. Okay. Yes. Oh my God. Okay, we've got milking cows and the cows fell over. Oh my goodness. Okay. So we need to think back to the beginning of 2023. Okay, 2023, a little over a year ago. Who remembers the small earthquakes, the swarm of earthquakes that happened out in the middle of the valley? Anybody? Raise your hand. Yes. Okay, at the very beginning of January, did anyone feel that? Did anyone feel those earthquakes? Well, yes. Yeah, you were living out here in Newton, so very close to these earthquakes that are denoted with this dot right here, these dots, okay, a whole swarm of them. So you might have felt them, okay. When the first earthquake happened, this magnitude 3.2, I was in my office, okay, in the geosciences building, and my dog was in the office with me. Her name is The Probe. And The Probe was laying down under my desk, and all of a sudden she stood up. And I looked, and then all of a sudden I heard like a sonic boom right after she stood up. That was interesting, okay? And then the building shook a little bit. I was definitely like, should we leave this building? It's an old building. But yeah, I definitely experienced one of the earthquakes in the Benson swarm, okay? So do any of you have friends on the East Coast, maybe in New England, in the New York area, that experienced the earthquakes in New York and in New Jersey, actually? It was in New Jersey. Yes? Yeah? I saw some other hands go up. Yes? Okay. So here's a text exchange with my friends from Wellesley College. This is my college group chat, all right? So check this out. Okay, This is Lindsay. Lindsay lives in New York. Here are the earthquakes right here in New Jersey. All right, was a magnitude 4.8 in New Jersey, this blue dot. And then after that, there were over 50 aftershocks. So when that magnitude 4.8 happened, Lindsay just had a teeny earthquake here in New York City. And Mary lives in Boston, okay? Mary was like, did you really? Oh my gosh, did you feel it? And Audra lives down in Texas. She lives in Austin. She was like, oh my goodness, are you okay? And Lindsay said, I definitely felt it. Mary said, oh wow, there was one here too, apparently. And so as this was happening, I'm like, oh my gosh, exclamation point, earthquakes in New England, all right? And for a while, I thought that there were actually 2 earthquakes that had happened. But I was digging around on the USGS earthquake page, and there was just one, but the ringing and the shaking was felt all the way up in Boston. And so Lindsay, she said, gosh, this was a little scary. Okay, she lives in New York City in a high rise. She said, I ran out of the building with the dog, but no one else did. And everyone is out on the street acting like nothing happened. And then she said, well, my colleague at work said, well, New Yorkers are hard. So they're toughing it out. Okay. All right. So in tonight's Science Unwrapped talk, we are going to investigate 3 questions, okay? We are going to investigate why earthquakes occur. There's a question. Yes.
I think it's because the earth sometimes shake a little and they cause damage to buildings, and bridges collapse. Usually it's because they had to stretch out because cracks appear on the ground and between them.
Okay, this is an awesome explanation of what's happening in an earthquake. Okay, we'll have one more and then we'll keep going. Go.
What usually happens is the earth's not shaking. The things that make up the earth tectonic plates are usually rubbing together, making these movements in the earth, making all the shakes.
Okay, y'all want to come down, both of you, and give this talk? Let's go. No, stay there, we're good. This is awesome. You're describing what is happening during that earthquake, and you're talking about plate tectonics for why earthquakes happen. We'll get there. This is super good. Okay, but we need to kind of nerd out on some basics, too, and think about this thing called the First Law of Thermodynamics, and investigate whether earthquakes obey this. We hope they do. It's a law, right? Okay, and then we're also going to think about how energy is transformed during an earthquake. Now, for much of this talk, here we are in Logan. Okay, so here's Logan. All right, we are actually going to travel across the Atlantic to Turkey. All right, to Turkey. So this is the country of Turkey. And this is the town of Kahramanmaraş, Maraş for short, all right? How many of you, I want to see a show of hands, remember the devastating earthquakes that happened on February 6th, 2023? Anybody remember? Okay, some people's hands are going up. We're going to learn a little bit more about the earthquakes in Turkey, and they're going to help us understand these energy transformations, okay? And we're going to first focus in on this pink box right here. All right, so zooming in, this is a topographic map of this portion of Turkey. And what happened was that there were 2 back-to-back large earthquakes that happened. The first was a magnitude 7.8. That's big. We're going to talk about how big in just a little bit. A magnitude 7.8 happened right here, it nucleated right here, or it started right there on this fault zone. And then it triggered 9 hours later, it triggered a second large earthquake, a magnitude 7.6, okay? These back-to-back earthquakes caused tremendous damage and loss of life. So in Turkey, over 55,000 people were killed. In adjacent Syria, over 7,000 people were killed. Over 300,000 people were injured. Something like 14 million buildings were destroyed. And the total economic losses to Turkey, all right, were on the order of 10% of Turkey's economy. This is serious, okay? And this picture of Maraş from the New York Times gives you an example of some of the damage, okay? In the aftermath of the earthquake, I traveled to Turkey with a team of scientists and worked along the earthquake zones, along the fault rocks like you see here. This microphone is going to drive me, I think, crazy. Oh my goodness. Okay, but here we go. So in addition to studying the fault rocks, I was able to observe the damage, okay, the destruction and the loss firsthand. This is unlike anything I have ever experienced in my life. Now, we were there in the summer after the earthquakes happened, okay? And they were in the process of trying to clean up all of the buildings that had been destroyed. And so that's what you're seeing here in this video. But some buildings were completely flattened, and many are uninhabitable. And these images are coming from the town of Doğanşehir, Turkey. All right, so let's come back to these questions, and I want to think about plate tectonics. Yes, exactly. Let's think about plate tectonics and why do earthquakes occur? All right, so this is a map. This is a map of the globe, and it's been spread out. It's been spread out onto this rectangle, onto the screen. So we've basically unwrapped the globe and put it onto the screen. And what you see are continents. These are outlined with these thin black lines. Here we are in Utah right here, this pink star. And there are also oceans. And the black lines on this map, these are the boundaries in between plates, okay? And so we can visualize what's going on here with a simple block diagram, okay? And what happens in plate tectonics is that these rigid plates that are covering our planet, they are moving because the mantle beneath them is flowing. The mantle beneath them is flowing, right? And so what happens is, in some places, like at mid-ocean ridges, you have plates pulling apart, and along some plate boundaries, you have plates going down into the mantle, mountain ranges and volcanoes being created, okay? All of this is happening all around the globe, and this is plate tectonics. Now, how does this relate to earthquakes, all right? Stresses or pressures build up in the earth as these plates are sliding past one another, all right? They're moving relative to one another. And that is happening especially at these black lines right here, okay? All along here, these are all plate boundaries, all right? And at a really granular level, earthquakes happen not only at plate boundaries, but they happen on faults. This photograph right here is showing you a crack in the ground. This happened during the second of the two large magnitude earthquakes in Turkey. And that crack on the ground, this earthquake, is paralleling, and it's right up against a fault zone. So this is evidence that earthquakes occur along faults. Now, how else can we think about this? All right, so this diagram right here has stress on the y-axis and time on the x-axis. And so what happens is that stresses build up or increase through time, And eventually, they're so high that they exceed the strength of the rock, of fault rocks, or rocks that are right along faults, and eventually that fault fails, okay? The fault fails, and that causes an earthquake. Now, in this diagram, at these stars, which are identifying when earthquakes occurred, when that earthquake occurs, that stress is released, okay? Notice that this line just drops right down. That stress is released, all right? Another way we can visualize this, beyond just a diagram, another way we can visualize this is if we think about what happens to a fence that crosses a fault, all right? So at the beginning, at time 1, right here, at the start, there's a perfectly planar fence, right? Okay. Before that earthquake, the stress is building up and the sides of the fault are getting strained, right? You can see this fence is starting to curve, and eventually the stresses are so high that that fence is gonna break, all right? And that's what you see right here. After the earthquake, the fence is broken at that point right there, time 3. Now, you might be thinking, do we ever see this in nature? It's just a cartoon. The answer is yes. So this is a photo from the magnitude 7.6 earthquake. And what you can see here is there's a fence. Let's go ahead and annotate this so you can see this a little bit better. Do you see the different fence lines? So it goes like this. See this blue line right here? Now it's over here, and now it's over there. All right? That is because there are actually 2 fault lines that are running through this photograph. And during the earthquake, it offset that fence line just like in the cartoon on the previous slide, okay? And in total, this fence was offset by over 20 feet, okay? Over 20 feet during this earthquake. So this definitely does happen. Okay, now this diagram of this pink curve going, the stress building up, dropping down, building up, and dropping down, it looks pretty simplistic, right? And in nature, things are complicated. And so a more realistic diagram might look like something like this blue curve right here. The stress doesn't always build up the same, okay? It doesn't always accumulate the same way. The amount of stress that's released during a given earthquake is not always the same. The strength of the rocks along the fault can change through time. And so what actually happens through time during many earthquake cycles is really complex. And that's why geoscientists are needed to study earthquakes to understand how and why they happen. Okay, I want to take a pause and ask if there are any questions so far. Any questions? Okay, I don't see any. Let's keep going. Got to think about the second. Oh, wait. Yes. What is, oh my goodness. Thank you so much. So the question was, maybe I can get this back on. It's hard to gesture when you don't have both hands. My gosh. So a fault is a crack in the ground or a place where 2 blocks of rock slide past one another, okay? Yes, so you know what was happening with those fences? I could have done a better job annotating them. Let's go back. No, this is a great question. So you know what? There is actually a fault line that is running right through here. You see that? There's like a fault line that had to run right through there in order for that fence to bend and then break. That's an excellent question. And so in this next photo from the field, okay, there are actually 2 fault strands. And that's what I was annotating here with these pink lines. And that's why the fence was offset. And what they're doing, the fence has been displaced by those faults. Did you have another question? That's okay. In the back? Yeah. Okay, can big rocks crash into people? During an earthquake, it's possible if you have rocks up on a slope and you have shaking of the ground, those rocks could tumble down. And if people happen to be standing there, they absolutely could crash into you. Because earthquakes can also cause or catalyze things like landslides that help move rocks. Absolutely. That's a really good question. Okay, let's go ahead and keep going here, all right? Okay, so we've got to come back to basics, all right? And talk about the first law of thermodynamics and whether earthquakes obey this. Okay, so the first law of thermodynamics explores, or I should step back and say thermodynamics, is exploring the relationships between work and other forms of energy, like heat or light, okay? And so the first law of thermodynamics says that energy cannot be created or destroyed. Okay, energy cannot be created or destroyed, but it can change forms. Okay, it can change forms. And so what we're going to do now is we're going to explore the different types of energy transformations, the different types of energy that are given off during an earthquake. These include seismic waves, okay, seismic waves, breaking of rock, and heat. Okay, the first energy transformation are seismic waves, all right? So in this block diagram, what you see is a fault. So this is a fault, and there's rock on either side, and during an earthquake, which forms at depth, the sides of the fault move past one another. And when that happens, they radiate seismic waves. Raise your hand if you've heard of seismic waves. Anybody heard of that? Some hands go, yes, seismic waves. Just from me, first time ever. All right, we're learning stuff together, that's awesome. Okay, so what are seismic waves? They're essentially sound waves that move through rock. So sound waves typically are moving through the air, that's why you can hear me, right? Okay, but sound waves that move through rock are seismic waves. And when an earthquake occurs, there are a variety of different types of waves that are generated. Some of these waves are called body waves, and they're traveling through the interior of the earth, okay? Some of these waves are surface waves, and they're moving right along and underneath the Earth's surface, and it's actually these surface waves that cause a lot of damage, all right? It's seismic waves that can cause damage, all right? So, seismic wave energy is related to this concept of earthquake magnitude. Remember early in the talk I mentioned the swarm that happened out in Benson? And you saw on the slide it said magnitude 3.2, right? And the earthquake that happened in New Jersey, right, that was a 4.8, 4.7. But then the earthquakes that happened in Turkey, those were on the order of 7.8, 7.6. Those were really big, all right? But how big? How can we understand this? Well, we can think about this in terms of kilograms of TNT, or explosives. Raise your hand, besides Dennis, if you have ever blown something up. Yes. Anybody blown something up? Yes. Dennis did that in college. Okay, New Mexico Tech. All right? But it's really interesting to think about how these earthquake magnitudes translate in terms of kilograms of explosions, okay? So, later in the talk, we're going to think about the Magna earthquake that happened down near Salt Lake City. That was a 5.7, all right? And that is equivalent to about 10 million kilograms of explosives. But the earthquakes that happened in Turkey Those are much larger. And note, look at this scale. It is just going through the roof. All right? Those are on the order of, oh my goodness, almost 50 billion kilograms of explosives. That is because this magnitude scale is what we call logarithmic. Okay? So every time you kick up a notch on this scale over here, you're going up by a factor of 32. All right? All right, here's a question for you all. We can see the effects of earthquakes. We can see the damage that happens. We can feel the ground shaking. Can we hear earthquakes? Can we hear them? What do you think? Yeah, can we? I think so. You think so? Okay, anybody else want to say yes? Yes, okay. So remember, I told you all at the beginning of this presentation that when the Benson earthquake happened, I heard this sonic boom, all right? So that's one piece of evidence, and maybe we can hear them, all right? But I'm showing you this photo here because this is a picture from Turkey, and after that first earthquake happened, many people ran out of their homes, okay? They were terrified. It was a magnitude 7.8, buildings were collapsing. And many of them then spent the next 9 hours outdoors. There was a man that was standing out in this field, and he told my colleagues that when that second earthquake hit, that magnitude 7.6, he saw it coming, and it sounded like a donkey screaming. So he saw it. He saw that rupture coming to him, and it sounded like a donkey screaming. This is another form of energy, actually. Okay, so as a geoscientist, we go out into the field, and we are out there documenting and observing other types of earthquake energy transformations, right? So the second type of earthquake energy transformation is breaking of rock, all right? Breaking of rock along a fault line. And so this is a picture of the magnitude 7.6 surface rupture in Turkey. You can follow it for kilometers, okay? This rupture even went through buildings. Okay, so look at this house right here. This rupture went through buildings, and it actually caused this entire building to shear. Right? Amazingly, in the weeks after this earthquake, it was still standing. Still standing. So it survived the rupture propagating or just passing right through it. These photos were taken by my colleague Sinan. This was taken 1 month after the earthquake. When we were there in the summer, the building had been demolished. Okay. Here's another picture of the earthquake surface rupture that was captured by a drone. How many of you know what a drone is? Okay, right? So the drone was launched with a camera so that they could take pictures, of the surface rupture. And what's really amazing about this is check out this road. Do you guys see this? Look what's happening to this road. It is actually being displaced or moved on either side of the fault by over 25 feet or 8.5 meters. Okay? It's remarkable. The other thing that's really interesting about this is you can see that in some places, the surface rupture, it's not just a single line, but it's really complicated, okay? So the way in which the rock is breaking is complex. This is a picture of the rupture interface. And along this rupture interface, you can see these grooves or striations that formed as two sides of the fault slid past one another, all right? So this is literally the rupture interface, and there are these grooves. And so my colleague Sinan took a sample from right here of the rupture interface. Now, as geoscientists, we want to make sure that we can observe evidence of these earthquake energy transformations at a variety of different scales. And so once we had this sample back here at Utah State, we were able to use a very special type of microscope that we have right here on campus called a scanning electron microscope to observe the sample of the rupture interface. And what's special about this microscope is it allows us to see things that we cannot see with our naked eye. So to put that into perspective, okay, here's what the size of, say, a grain of beach sand might be. Here's what our naked eye can see. And then here's what a microscope can see. A microscope can see things that are 1/1,000,000th the size of a meter. Okay, 1/1,000,000th. So here's a micron, all right? Even tinier than bacteria or even tinier than a red blood cell. When we bring that sample into the lab and look at it with the scanning electron microscope, this is what we see. Raise your hand if you can see striations on this surface. Anybody see that? You think you see that? Striations. What are striations? What are striations? Do you know? What are striations? Does anyone know? Lines. Lines or grooves that form as the two sides of the fault slide past one another. Think about this. Let's put our hands together, right? Our knuckles would be like the striations that form on a fault surface if the two sides of the fault slid past one another, okay? So there's the fault is rough, and as it slides past one another, it's making grooves on that rupture interface, on that fault interface, okay? Another important thing about this image is, as geoscientists, we always like to put scale bars on our images. It says 20 UM. This is the Greek symbol here, right? 20 microns. 20 microns. So that is 20/1,000,000ths of a meter. We are way zoomed in. We are way zoomed in, and we need this microscope because we could not see this with our naked eye, all right? And so what we see on this surface is we see the striations, these grooves right here, and we can zoom in even further and see that this material is made up of not just microparticles, but even smaller particles called nanoparticles. Because this rock has broken and ground down during that earthquake to make really, really tiny particles. And so this is an example of an energy transformation, the energy that goes into breaking the rock and grinding it down. All right. So let's talk about this sample right here. You guys see this? Let's talk about this sample right here. This is a fault rock. You guys see this? How do we know? How do we know? I'm telling you, this is a fault rock. Why? What about it looks like a fault rock to you? Yeah. Oh, it's glossy from friction. What else? Yes, it's planar. It's planar. It's glossy from friction. Yes. Yeah, so something has rubbed along the other side, but it's gone. I wish we had the other side of this. Oh my goodness. Yes?
It's kind of shiny.
Shiny. Okay, shiny, glossy, all right? There's actually striations or grooves on the surface, okay? This is this sample up here. So again, as geoscientists, we collect samples, we bring them back into our labs, and we want to investigate them at a variety of different scales. And so what my former undergraduate researcher Jordan did was he cut this rock with a saw. Okay, Jordan, you did this. Yes. He cut the rock with a saw so that we could make this specimen right here, so that we could examine it with the special microscope. In essence, what we wanted to do was cut the rock open like you would cut open a cake, all right, so that we can see the inside. And then we took it into the lab and we investigated what this fault surface, this is the fault surface right here, what it looks like with the microscope. And this is one of those images. Okay, now, note the scale bar. Note the scale bar. 2 microns. This line right here is 2 millionths of a meter. What's a meter? My step isn't quite a meter, but 2 millionths of a meter. Yeah, it's really tiny. And what we observed were these beautiful, beautiful crystals. You guys see these beautiful crystals? And the really interesting thing is that in between the crystals, like right in here, some of the crystals have been plucked out, but we actually observed melt. We observed melt. There was quartz melt in this hematite-rich rock. Who's heard of hematite before? Anyone? Jim. I know Jim has. Jim is an expert on hematite. Jim, what does hematite tell us? It's iron oxide. Iron oxide, so there's iron and oxygen. This is what helps make rocks red. Okay, have you ever been to Moab? Been to Moab or maybe St. George? And you see lots of beautiful red rocks? There's all this hematite in there. And when you have enough of it, when you have enough of the hematite, okay, it actually is black. This rock is all hematite with a little bit of quartz, okay? All right? So, when we look at it with the microscope, really zoomed in, we see these amazing hematite crystals, and in between the crystals, there is silica melt that was preserved. If something melted, what does that mean about the temperatures that it might have experienced? If something melted, if this fault surface melted, what does it mean? High temperatures, low temperatures? What do you think? Yeah. High temperatures or low temperatures? Very high. Okay, we're not just going to say higher, we're going to say very high. So this is actually another energy transformation that heat is produced during the earthquake that happened on this fault surface, okay? How hot do we think that this fault surface got? Very hot, but what kinds of numbers? Well, actually, we think it got as hot as 2,100 degrees Fahrenheit, way hotter than boiling water, right? Or 1,200 degrees Celsius, hot enough to melt the rock right at the slip surface, and then the temperatures dropped, and the beautiful crystals grew, and some of that melt was preserved. Okay, so let's think about our 3 questions and go through and answer them as a way to wrap up. So, why do earthquakes occur? They occur because of plate tectonics, this fundamental thing that is happening on our planet all the time, okay? Stresses are building up because of plate tectonics, okay? Stresses are building up, and once those stresses exceed the strength of the rocks on either side of the fault, they fail and an earthquake happens. We learned about the first law of thermodynamics, right? And whether earthquakes obey it. And the answer is, oh my goodness, yes, earthquakes do. We sure hope so, okay? And that first law of thermodynamics tells us that energy cannot be created or destroyed. It can only change forms. And as it pertains to earthquakes, there are different ways that energy is transforming during what can be catastrophic events. You have seismic waves that are given off, you can break rock, and you can have heat that's created. All right? Okay. Now, what about here in Logan? What about in Utah? Do we have to worry about earthquakes? Yes. Okay? So, this is a map. Here is Idaho, Utah. Here's the Wyoming border. And what this map is showing you, it was made by the US Geological Survey. What this map is showing you is where all of the major fault lines occurred. Okay? Cache Valley, see this? Cache Valley is right here. We are located right here. This is the Wasatch Fault. How many of you have heard about the Wasatch Fault? Anybody? Some people, okay. The Wasatch Fault runs all the way from Idaho down through Utah, and over 80% of our population lives very close to the Wasatch Fault. And the reality is that these faults are seismically active. That means they're able to produce earthquakes. These faults that are colored here, including the Wasatch Fault, the West Cache Fault Zone, and this is the East Cache Fault Zone right here. In our lifetimes, in many of our lifetimes, there is a greater than 50% chance of a magnitude 6 earthquake that would happen in the next 50 years. Okay? That is the probability, and this is what has been put together by the US Geological Survey and the Utah Earthquake Probabilities Working Group. All right? Now, have there been any earthquakes recently on the Wasatch Fault? What do you think?
I would say probably a lot of earthquakes happen like all the time, but a lot of them are way too small for us to even notice. That's why humans have created this machine that can measure earthquakes and know when one's happening.
Yes. Okay, let's say that back. There are earthquakes that are happening all the time, okay? But oftentimes they're so small that we can't detect them. That's why we have seismometers and different instruments. The machine that you mentioned, seismometers that can detect those seismic waves, okay? So there probably are tiny earthquakes that are happening. What about a big earthquake? Do you all remember the Magna earthquake right as lockdown started? Do you guys remember that? It was in the morning. I think it was like March 20th or something like that. We were all at home. Did anybody feel the Magna earthquake? Some hands. Anybody feel that? Gary, yes. Some people. Okay, I felt the Magna earthquake. I was sitting at my desk. Okay, I was sitting at my desk, and my chair started to roll side to side. Okay? And I was like, whoa. And I think that some of our faculty, we started texting. I believe Jim and Suzanne, you might have sent, did you feel it? Did you guys feel Magna? And we started a text message because we were like, oh my goodness, we just felt an earthquake, right? Here in Cache Valley. That earthquake happened down near Salt Lake City. Okay, here's Salt Lake right here. That earthquake was a magnitude 5.7. Its location is here with this yellow dot. Okay, that 5.7 is like 10 million kilograms of explosives going off in the earth, okay, causing those seismic waves, causing all these energy transformations. And then all of these red dots are smaller magnitude earthquakes or aftershocks that happened after the 5.7, all right? Now, this is a pretty large magnitude earthquake. And we think that it occurred possibly on the Wasatch Fault system, but it's not quite large enough to reset the earthquake cycle, to relieve the stress on the Wasatch Fault. And so the likelihood of a very large earthquake on the Wasatch Fault or any of the nearby structures remains high, okay? Even though this happened, all right? And so in today's talk, in tonight's presentation, you all learned about earthquake energy transformations. Earthquakes are complicated, earthquakes are complex, and the reason why we as geologists, as geoscientists study them is because we still don't fully understand why they occur. We don't understand all of the energy transformations. And if we can make inroads, if we can make progress on those problems, we can better understand the potential risks to our lives, to the built environment, and we can mitigate against them. And so I want to thank you all, and I will take any questions that you have.
Great, thank you, Alexis. And okay, so I hope you are thinking of questions for Dr. Ault. But let's take a pause. I want to tell you before you all disperse that next year, for next academic year, there's a new theme for the Science Unwrapped talks, and it is joining forces, which I think is cool. It's going to be about scientists teaming up, different kinds of scientists who team up to solve problems using different sorts of techniques. So we hope we see you all here next year. So please think of questions and hold on. In about 30 seconds, we can start asking Dr. Ault questions, but also anybody who wants to go ahead and leave now and head out in the hallway, get a beverage, and check out some of the activities, go ahead and sneak out now. And then we'll start questions here in just a little.
So one of the things that I've heard, and you know what, maybe even Joel, you can correct me on this, we're talking about the New Madrid earthquake, is that, I see how I can explain this. So remember we learned about, in tonight's presentation, we learned about plate tectonics and how the mantle is flowing, okay? Right. And that mantle can even put stress on faults that are way far away from plate boundaries. So the truth is, the earthquake that happened in New Jersey, that's not near a plate boundary, but it's a very similar thing, right? Where you have this mantle that's flowing and the plates are really rigid, and that puts stress on these faults, and then eventually they're gonna fail, okay? Now, one idea that I learned about in graduate school, and oh my goodness, I feel like I shouldn't even say this. You might say, why is the mantle flow? Well, the mantle always flows. Right. But what I learned was that there's flow related to isostatic rebound of the Laurentide ice sheet. Okay, so basically, think 2 million years ago, much of the northern hemisphere was covered in ice, in a big ice sheet. And when you melt that away, basically the whole Earth is breathing, like it just rebounds. The surface is rebounding, and the mantle is flowing beneath the plates to accommodate that and adding that extra stress to those faults, right? So that's what I learned about the New Madrid earthquake. Yeah, it's very interesting, but yeah, very cool, awesome. Are there other questions that people have? Oh my, yes, let's go here, and then here.
The object of earthquake mitigation.
Here. Yep.
The object of earthquake mitigation at the Salt Lake Temple, is that to keep energy from being transferred to the building?
That is a great question. The question was about how the temple has been retrofit. And the truth is, I do not know all of the details of the temple's retrofitting, but I would imagine that they're paying attention to how that building might vibrate or shake during an earthquake, what its frequency is of shaking, and then trying to retrofit the building to accommodate certain levels of seismic waves. But this is not my... Well, I don't know whether they did that. I don't know. Suzanne, do you know, or Jim, do you know about the retrofitting to the temple? I don't. So we have actually here, just to say, at USU, there is an earthquake engineer. His name is Brady Cox. And if he was here, he would know the answer to that question. But we have the expertise here at USU to answer that. And what I would just say is that the people, like earthquake engineers, what they're trying to understand is how certain types of buildings of certain size and certain material will vibrate and respond to certain types of seismic waves and their frequency, and they might be retrofitting the building to take into account the ability to withstand a 6, a 7, a 7.5, or something like that. Yeah. That's a really excellent question. I'll just say one other thing. When I was in Berkeley, I went to Berkeley this summer for work, and when I was there, I actually saw this building that has been retrofitted to actually move like what you just described, to slide like that. And it's right near Cal Berkeley campus, and that was the first time I had ever seen something like that. But that's near the San Andreas Fault in California, and so they're thinking about that stuff. But just what you described about a building being able to move, I've seen it. I don't know if that's happened to the temple, though. Oh, go ahead.
I was in the Banning earthquake.
Oh, whoa.
I was up on a lift truck replacing light bulbs in a big sign, a video board, and the bucket crashed into the sign, and I yelled down to the guy, I says, knock it off.
Oh my gosh.
And he didn't feel it, but the resonant frequency was slow enough.
Oh my gosh.
Slammed right into them, and it knocked out hundreds of bulbs, and then it went back and it smashed into it again, so
Oh my goodness.
I just held on.
Oh my gosh, that's amazing. Okay, yes.
Do you want me to use the mic or no?
Yeah.
I'd love
Yeah.
to. Are you familiar with the seismograph of the Tuckaleechee Caverns in East Tennessee?
No, oh my goodness, no. But tell me more about this so I can understand.
Okay, so it's caves in East Tennessee, and when we went there, they said they had one of the primary anchors for seismography in America
Huh, okay.
because of the weather control within the caves and some.
Oh, that makes sense. And being underground a little bit? Yeah,
So I just wondered if you're familiar with it.
I am, that is really neat. I am not familiar with that, but I could see the potential utility of something like that, of instrumenting a cave with things that can detect earthquakes. Because, right, these could be earthquakes that are happening, like the Turkey earthquakes. I bet that the seismographs detected that. Actually, in the midst of the Benson swarm here in Utah, the University of Utah's geophysicists and their seismic network, they reached out to folks here at USU, okay, and they were very interested in putting instruments here in Cache Valley because we don't have enough instruments to record any earthquakes that might happen, okay? And so because of where I live on close to bedrock, right near the mountain front, in between two strands of the East Cache Fault, right where I live, we volunteered to have an instrument put into our garage. It was really cool, except immediately after they installed it, the earthquake stopped. So all they have in their instrumentation is like the garage door going up and the garage door going down and the garage door going up. So, I mean, we came really close to being part of science, but yeah. Are there other questions? These are really good. Yes.
It's hard
Okay.
for me to understand during
Okay.
an earthquake.
Yep.
Something slides, something
Yep.
like this.
Yep.
So why does it keep vibrating over and over for minutes and minutes? Are these doing this, or is it just sliding and then they're?
This is an excellent question. So this is a question about what is happening during an earthquake along a fault, and what is the relationship between that and then the earthquake and like basically the shaking that happens. I want to just actually go back to a diagram that I had maybe. Okay, let's come to this diagram. Now, this is not exactly the setup that you're thinking of because you're talking about a strike slip fault where two sides slide past, but it could do that too. So this is a normal fault right here, which is like the East Cache Fault that we live by, or the West Cache Fault, or the Wasatch Fault. So what happens is when you have that earthquake nucleate, and it's nucleating at this location right here, it's a, at the depth. So we have to know the depth at which these occur. And we use seismographs and things like that to figure that out, like the one in Tennessee. Okay, so at depth, that earthquake nucleates, and when that nucleation happens, it sends seismic waves. It sends these waves radiating out through the interior of the Earth. That's the focus point. Those seismic waves are radiating out, and actually, I didn't get into this, but what happens is this rupture grows outward. It's going to grow up the dip of the fault, it's going to grow down the dip of the fault and outward, and that is where that slip happens that you're describing along the plane, okay? So seismic waves are given off and they're radiated and they're traveling through the interior of the Earth or underneath, like right along the Earth's surface. Those are the different types of waves in this diagram right here, okay? Body waves and surface waves, okay? And we have a demonstration out here where we can play around with the different types of waves. But the other thing that happens is that you have energy released as those blocks of the fault slide past one another, and that is happening along that fault plane, okay? And sometimes, you know, the seismic waves are being radiated in all directions, but depending on the orientation of your fault in space, that is going to dictate how the two sides slide past one another, okay? But the shaking is due to the seismic waves. That's what's causing the damage in the shaking, the surface waves in particular. That's an excellent question. Yeah, it radiates out, and you have that shaking. And that's why early in the presentation when I said my friend Lindsay was very close to New Jersey. She was in New York, but people in Boston apparently were feeling it, okay? Just like the earthquake that happened down near Salt Lake, we felt it here in Cache Valley, okay? That's the seismic waves radiating and the shaking being felt. And the larger the earthquake, the further away you feel that shaking. Yeah, that's an excellent, excellent question. Yeah.
When that escarpment happens,
Mm-hmm.
does that happen in 1 second, or does it go slow?
Man.
Does it vary? Really fast? Slow other times?
Okay, so this is an excellent question that has to do with how fast a scarp forms, okay? And is it happening, what is fast? So an earthquake slips at a meter per second. It's like, boom, a meter per second, right? And the answer is, it depends. We have some evidence from the rock record that slip must be really fast, like a meter per second, okay? We have some evidence of that. But in other cases, it actually might take a few seconds for that scarp to ultimately form, all right? There's another complexity to this that is the scarp forms at a certain rate, but that rupture is propagating at miles a second, miles and miles a second, okay? So the actual earthquake is going through the earth so fast, okay? The crack is propagating so fast, but the slip behind it, because of the friction, might be a little slower, maybe a meter per second, maybe less. That's an excellent question. It's really good.
And several earthquakes, including Yellowstone, and then the one that happened in the 1980s at Garden City. I was at my house, and the house just went over like this, one thump,
Whoa,
no shaking.
just a boom.
The piano
Yep,
slid out from the wall.
amazing.
Set collection, and my potted plant fell off the piano. The piano nearly tipped over, but it did. It came out from the
Yeah.
wall about 24 inches, and it was like a truck hit the house. It was like boom.
Boom. Yeah. Amazing. It reminds me of the sonic boom that I felt from the Benson earthquake. And then there was a little bit of shaking, but it was really that boom. I don't know. It's really interesting. You had another? Do you have guys? No?
There's more to comment.
Yeah.
So I have a friend who lived in San Francisco during the earthquake in the late 80s, I think it happened.
Okay.
She said the roads,
Oh my goodness.
she could just see the roads
Oh,
leading.
oh my goodness. Yeah.
Can I follow up on this
Yeah.
question? When we talk about the magnitude,
Yep.
talk about the energy that's
Yes.
in the earthquake, is that over, what's the time period of that energy
Okay.
transferred? Is that, well, what's the time frame and what's the area of it, right? Are we talking about like, right at the focus? That's the energy being released right there? That doesn't seem very.
Okay. Okay, this is an excellent, I love this question. This is a question about earthquake magnitudes and how we assess how much energy is being given off. And you said a couple of things there. You're thinking about time, over what time. So, as an example, in Turkey, the magnitude 7.8 that happened, that event happened over 90 seconds. That happened over 90 seconds. And that is because that earthquake ruptured, meaning it broke the rock and moved along a fault and propagated along a fault over 300 kilometers. So there's a relationship between the size, which was another thing that you mentioned. Let's just come back to this map right here. There's a relationship between how much of the fault ruptured and how long it will last, okay? But it's actually kind of even more complicated than that, though, because this second earthquake that happened, the magnitude 7.6, the back-to-back earthquakes, this rupture was not, this red line indicates the fault that ruptured. It was half of the first earthquake. It was half. But the amount of energy that was released was just as much, and some people think even more, because at depth, how much was rupturing at depth and how much energy was maintained as that propagated versus being lost to all the different sinks, like breaking the rock and heat and all, so it's complicated because there's a general relationship between earthquake size and what we assess from like seismographs, like a 7.8 versus a 6 or a 5. Between that and the true amount of energy that's given off, like how many of those explosions, and there's a variety of factors that go into that. Mostly geophysicists assess this based on the seismographs and the seismograms that are produced from the seismographs, so the instrument in Tennessee in the cave, from things like that, and also using satellites to see how much the Earth has distorted after the earthquake. So they look at images of Earth. But that's a great question. It's complicated. Yeah, go.
So when we say 7.8 or 7.6, what we're really saying is we're kind of estimating the total energy over the entire.
Yes. Yes.
Movement. I've also heard a magnitude applied to an earthquake at a distance from the epicenter. So like I was in the Idaho earthquake, 82, 83. I remember it being a 7 point something up in the mountains. I was in Boise. My desk was shaking in school.
Yeah.
I remember them saying in Boise it was a 4 point something.
I've never heard, I also haven't heard that. They usually say it at the source, and there's different ways in which that rating scale has been assessed. Like it's a 7.8 or 4, like that. There's different types of moment earthquake, like the earthquake moment and the moment magnitude, right? And there's different ways to do that, but it always relates to the source. Yeah, did you have a question? Yeah.
Back when you said the percentage of an earthquake happening in 50 years,
Yeah.
how are we getting the whole 50 years? Why not tomorrow?
Why not tomorrow? Well, okay, so it's all, okay, excellent question. So let's go let's go here. Yeah, that's the whole thing, is it's not that, I should be really clear here, it's not, it's probabilities. The likelihood, the chance. This was, I think, last week or month's Science Unwrapped. Ability and chance. So there's like basically a 50-50 chance that in the next 50 years, and that includes like tomorrow, 10 days from now, a year from now, 49 years from now, that there's going to be an earthquake of that magnitude, 6.
Is it increasing as time goes
Well, but so here's the thing, is that it's not, the way that they think about that is not necessarily that the chance is increasing, it's over a given time window. And what the US Geological Survey is saying is that within that 50-year window, this is this is the likelihood, 57%, or I think it's something like 43% for a magnitude 6.75, or a larger magnitude earthquake, but it's just a probability. Yeah. But I think you're making a really important point about if a fault ends up being overdue, like it should have already happened, and there's some faults where we know from the history of past earthquakes, they should already have had another one, right? The San Andreas fault is an example of that, where it should already have happened, but it hasn't happened yet. So it seems like, aren't we more likely to have it?
That's gonna make it bigger. If it builds up farther,
It has the potential to be bigger. It's complicated, but it has the potential. Right now, what they're saying is this is just the probability of, like, in your lifetime, 50-50, that there would be a magnitude 6 on any one of these structures, basically.
Not like the in my lifetime part.
I know, but this is the thing, is that you can be prepared, right? You can be prepared. Lots of people in Utah are prepared. And, you can, when an earthquake happens, you can stop, you can cover yourself, right? And you can grab onto something and stabilize yourself, protect your neck and head. There's all things you can do.
I'd rather get out of the house.
I know, well, I thought to myself when the Benson thing happened, I was like, should I get out of this building? But what the advice is to stay put and to seek a position where your body is going to be protected. Be in a doorway, go under your desk or something like that.
Seems like the most likely place to collapse.
But it has that reinforced siding or something like that, right? And then here's the thing. So when get this, I'll tell you, the truth is, when I was in Turkey, we went there. The first night we were there, we experienced a magnitude 4.8. 4.2. Yeah, 4.8. The next night, 24 hours later, 5.3. No, I was like, oh my gosh, well, this place just had a 7.8. Oh my goodness, are we building up to something else? And I honestly I didn't know what to do. And what I should have done was exactly what I just described to you. And in the end, we were like, what do we do? What do we do? And we were in a hotel on the 6th floor of our hotel. And we ended up going outside and sitting outside for a while. So it's okay to feel uncertain. It's okay to feel scared because it's a tough thing.
Why wouldn't you want to be outside or nothing can hit you?
Well, that's the fear is that by the time it takes you to get outside, there's been structural damage. And so that's why they want you to stay put.
So
But
be covered by debris and trapped there.
well, but here's the thing, is that if you find something, that's why you need to be prepared. There's actually, when is the shakeout, Joel? It's just coming up. Next Thursday at 10:15 in the morning, you can practice. We're all going to practice at 10:15 in the morning. We're going to stop and do whatever. I'm going to be in my office, and so I am going to not get under my desk because it is like IKEA cardboard. So I'm not going to do that, but I'm actually going to go to my doorway because that's pretty stable. And then after like 30 seconds, I'm going to get out of the building, right? The thing is, if there's shaking and you're still concerned that things could collapse, but the shaking stops, you can go then. The advice is to then move and go out of the building. So it's okay to leave.